Hi, everybody. Welcome back to the Feynman technique. Today we'll be continuing our series on the power of complex numbers, and today we will be evaluating these two generalized integrals right here. And you may notice that I have actually derived this expression before on this channel. The method I used to do that before was much more difficult and involved than the process I'm going to show you today, and we'll be getting an extra integral out of it during the process. That is this integral right here. So we're going to be finding closed form expressions in terms of t for both of those integrals. All right. Now, as in all the previous videos in this series, we are going to start with a known value. That known value in this case is this generalized expression right here. I've derived that on this channel in several videos before. I'll try to find the best example and link to that video in the description. But for this video, we're just going to be taking that as true. And I did not write this here, but this will be true for the real part of t being greater than 0. All right, so continuing, we'll create a new integral right here. All I did was replace this 1 with an a squared, and then I set it equal to, it's the same thing, just with the a 1 over a squared factored out. And then we let u equal x over a, x equals au, dx equals a du, and perform that substitution to give us this. So this integral is equal to this integral. All I do is plug in the substitution right here, and that's going to be equal to pi over 2a times e to the negative at. That just comes as a directly from this, our starting known value right there. Notice we just have tx here. In this case, we have at. So we just replace this t with an at and divide by a. All right. So next, we are going to let our a equal e to the I pi over 4. And remember I said that this integral, this will converge for t values, for t values, or in this case, at values, whose real part is greater than 0. And if we plug in a is equal to e to the I pi over 4, that will be satisfied. Okay. So continuing on, we are going to plug a equals e to the I pi over 4 into this expression right here, giving us this. You can see all I did was plug in a equals e to the I pi over 4 right here, and that's just going to give us I. And then that is going to be equal to this, where a is equal to e to the I pi over 4. You can see that we still have the pi over 2 right here. Our a in the denominator will become e to the negative I pi over 4, and then this becomes e to the negative t times e to the I pi over 4. And then I do some simplification. I combine exponents. This utilizes the property that a to the b times a to the c is equal to a to the b plus c. That's just right here. And then I rewrite this e to the, just this e to the I pi over 4. I break that up into its cosine and sine parts like this. All right. And then next, I just continue with the simplification. You can see I took this and combined them and then separated the real and imaginary parts. And then I split it up into two exponentials, one being this one, that's e to the negative t squared of 2 over 2 right here. And then we have e to the negative I times t square root of 2 over 2 plus pi over 4. And you can see I also took the values of cosine pi over 4 and sine pi over 4, which are both square root of 2 over 2. All right. So now we're here. Don't forget that this expression was equivalent to this integral right here. All right, and this integral we can get from here to here by multiplying the top and the bottom by x squared minus I, giving us x to the fourth plus 1 in the denominator. And then what I did is I used Euler's formula on this to break it up into its cosine and sine parts. That's right here. And we are pretty much done. Now all we have to do is match the real and imaginary parts of this integral with the real and imaginary parts of this expression right here to give us this. We are done. This integral right here converges or evaluates to this, and this integral right here evaluates to this. All right, guys, I hope you enjoyed that, and we will see you next time.